Hello everyone. Today we will continue the discussion regarding complex numbers, and we will talk about representation of complex numbers. Up to this point, we know one representation of complex numbers. We know we know that we can write any complex number as a plus b times j, right? Or I could write it as a plus j times b. Right, and this is a very straightforward way of writing complex numbers, and we know how if I have two such complex numbers, let's say I have z1 and z2, I know how to add z1 and z2 to get a third complex number, and then I know how to also multiply z1 and z2 to get a third complex number, call it z4, a different complex number. All right, and then the nomenclature here for those components of the complex number are as follows. So if you have such a complex number, you have what's called the real part of the complex number. Let's call this z. Let me write this properly, z. So the real part of z is going to be a, and then the imaginary part of z is going to be b. So a is called the real part and b is called the imaginary part. Okay, there is a special thing we haven't discussed. So we discussed adding complex numbers together to get a third complex number, and we discussed multiplying complex numbers together to get a third complex number. We did not discuss dividing complex numbers. Can we take two complex numbers and divide them, or take a complex number and invert it, right? So to do this thing, this operation, this division, I have first to introduce one basic operation that we can do to complex numbers that results in a peculiar gives us a peculiar result. Okay, and that basic operation that we can do to complex numbers is conjugation. What does it mean to conjugate a complex number? If I take a complex number and that equals, let's say, a plus jb, and I conjugate it, conjugation is designated by star. Conjugation essentially means just take the imaginary part and multiply it by -1. That's all that is. So this gives me a minus jb. Okay. Why am I bringing this up in terms of division? Well, conjugation has a very unique property. If I have any complex number, a plus jb, and I multiply that number by its conjugate, a minus jb. So this is z, this is z star, and I apply the rules of arithmetic. Remember, we said we apply the rules of associativity, commutativity, and distributivity, right? So if I do this math, do this multiplication, I end up with a squared, and then a times minus jb, so it's minus jba, and then plus jba, plus jba, and then j times minus j is what? J times j is -1. What's minus j times j? That's clearly 1. So j times minus j is 1, so I end up with b squared plus b squared. This cancels with this, and I end up with the complex number. It turns out that the complex number times its conjugate just gives me the real part squared plus the imaginary part squared. Okay. So conjugation, if you take a conjugate of any number, complex number, and you multiply it by that number, you get a real number. So this is always true. A number times its conjugate gives me a real number. Right? And this instantly tells you how to divide complex numbers or invert complex numbers. How? Well, let's say I have 1 over a plus jb, and I want to invert this complex number. right? I know what do I need to do, right? If I want, what I want to do is I want to have a complex number on top and have some constant on the bottom, right? So some real number on the bottom. So the best way to do that is to just multiply by the conjugate, right? So I multiply it by a minus jb over a minus jb. That's where conjugation becomes useful. This multiplied by its conjugate, we know this is equal to just a squared plus b squared, right? And then this is a minus jb. So instantly I know how to invert a complex number. The inverse of that complex number is just a over a squared plus b squared minus jb over a squared plus b squared. And instantly I know how to divide two complex numbers. So if I have a plus jb divided by c plus jd, right? I know the first thing I need to do is I want to conjugate, multiply the denominator by its conjugate, right? So I end up with a plus jb times c minus jd over c plus jd, c minus jd. I didn't change a thing. I just multiplied the numerator denominator by 1 over 1, or c minus jd over c minus jd, right? So I end up with, this is what? This is c squared plus d squared, right? The basic property of multiplying a complex number by its conjugate. You should always have it in your mind, okay? And this we can manipulate. This is going to be a times c, and then this term times this term, j times minus j is 1, plus b times d, right, plus j. This is going to be bc minus dA, and then bc minus dA. Okay, and this is the result of this division. Dividing two complex numbers gives me this equation, AC plus BD. Let me separate the real and imaginary parts. So this is the new complex number, BC minus DA over C squared plus D squared. And I can do this through conjugation. Conjugation opens the door to simplifies the process of dividing complex numbers with each other and inverting complex numbers. Okay. There's something curious here. Notice that a complex number multiplied by its conjugate equals a squared plus b squared. Well, let me write it in terms of the real part. Equals the real part of a squared plus the imaginary part, the real part of z, sorry, plus the imaginary part of z squared. This has a very suggestive form. What does this remind you of? This reminds you of the Pythagore, or I forgot how to spell Pythagoras. The Pythagoras theorem, right, for a triangle. So you have the sides squared equals, you sum them up and you get the hypotenuse squared. So this term seems to be the hypotenuse of something, some triangle. So it is then one interpretation of complex numbers that we could apply here using this is that we could imagine that the real part of the complex number and the imaginary part of the complex number are sides of a triangle, right triangle with 90 degrees angle, right? And this is going to be, this real number here is going to be the hypotenuse. Okay, so this opens up a geometrical interpretation of complex numbers or representation. Right? We could imagine the real parts of the imaginary parts of the complex number as lying on an orthogonal axis. So we could imagine that the real part of any complex number is kind of like lying on an x-axis, and the imaginary part is lying on a z-axis, and then each complex number is a point in the z-plane. So so unlike real numbers, where the real numbers could be imagined geometrically to live on a line. So this is the line of real number line, right? We could imagine geometrically that complex numbers live on a plane, right? Where the x-axis of each point is the real part of the complex number, right? And the y-axis is the imaginary part of the complex number. This is a valid interpretation. And then if we take a complex number and multiply it by its conjugate, we get a number, this real plus imaginary squared, that seems to be the hypotenuse squared, right? So this hypotenuse here, this distance from the origin to the complex number, to the point representing the complex number, is z prime, right? Square. So z hat, sorry, z star is the real part squared plus the imaginary part squared. But according to the Pythagoras theorem, this hypotenuse is the square root of that, real squared plus imaginary squared. So this concept, this hypotenuse can be called the magnitude of the real number, magnitude of complex number. Right, and we designate it with those two lines, right? So we have the z complex, right? So the magnitude of any complex number, or the modulus, this is also called the modulus. This is a useful value. It has a geometrical interpretation, as I've shown here, right? And it turns out that this modulus is simply z star square root. This is a basic property of the modulus. Okay. So this is like this is the same, by the way, representation of complex numbers, a plus jb, ultimately leads us into this geometrical interpretation. And because this geometrical interpretation is sort of like a Cartesian coordinate system, the real part and imaginary part are 90 degrees with respect to each other. We represent each complex number as a point on the plane, right? So this form of the complex numbers, this representative form of the complex numbers is called the rectangular form. It's the Cartesian coordinate form. So when we represent any complex number with its real part, which is kind of like the x coordinate, analogous to the x coordinate, and this is analogous to the y coordinate in a Cartesian system, we call this form of representing complex numbers the rectangular form. Okay. The basic thing we can see from this representation of complex numbers is that there is no meaning for order in complex numbers, because in real numbers, remember, all the numbers lie on a line. So we can talk about certain number being larger than another number. So certain R1, R2, we can say R1 is larger than R2, right? There is no magnitude, there is no meaning for two complex numbers for one to be larger than the other. What has meaning is the magnitude being different. So we could say that magnitude of Z2 is larger than magnitude of Z1. But there is no meaning for Z2 being larger than Z1. That has no meaning. Okay. Another way of stating this is that complex numbers are not ordered. Okay. So complex numbers are not ordered. Okay. This is the first major representation of complex numbers. The second major representation of complex numbers can be derived directly from this geometrical interpretation. right? Because now we've interpreted complex numbers as points on a plane. And there's no reason to designate points on a plane by their x and y coordinates. That's not the only way of designating points on a plane, right? That's one way, using the Cartesian system, which gives us the rectangular representation or the rectangular form which matches the original definition of the complex numbers, right? But I mean, there are many other ways of representing points on a plane. One way is the polar system, polar coordinate system, where we represent the point by a magnitude and an angle, right? A magnitude m and an angle is enough to uniquely represent a point on a plane. So therefore, a magnitude and an angle should be enough to uniquely represent a complex number. Same way where the x component and the y component are unique ways of representing a point in a plane, they are a unique way too of representing a complex number. Remember, we're in this geometrical interpretation, a point in a plane is a complex number. So this opens us up to another way of representing complex numbers, which is what's called the polar representation. Okay, and all that requires is knowing what is the polar representation of complex numbers. What does that, like that's fine. I mean, I could find a complex number as a point in a plane, and I know its magnitude and I know its angle. That's fine, and that's useful. I could also know the x component and the y component. The question is, for this to be really useful, I need to be able to have a way of switching between representations. Because let's say you are manipulating complex numbers and everything you are manipulating is in rectangular form, rectangular representation, right? But then you have some complex numbers that are in polar representation. Right? You want to be able to combine those numbers together. So if I have a complex number in rectangular representation and a complex number in polar representation, those are still complex numbers, right? I can add them together. So I should be able to add Z1 to Z2 and get some third complex number in any representation. So what you need to do is you need to have ways of converting complex numbers or transforming complex numbers from one presentation to the other. So you should be able to, if you have a complex number that's represented in polar form, you should be able to move it or transform it to rectangular form. If you have a complex number that's represented in rectangular form, you should be able to transform it to polar form, right? And then once two complex numbers are of the same form, you can add them together easily, and then or you can multiply them with each other easily. Okay. There's a subtlety there, and I will talk about it next, is that in rectangular form it's easy to add, but multiplication is more complex, more complicated. We have to think of a bunch of terms. It turns out that in polar representation it's easy to multiply, but addition is harder, right? And we will talk about this just now. The fact that multiplication becomes easier in polar coordinates or polar representation is something we have to show, of course. I'm going to show you that after we do the transformation from the rectangular form to the polar form and vice versa. I mean, the transformation itself can be argued from geometrical considerations, right? So let me draw it again. So I have the rectangular form, real and imaginary. Then I have a certain complex number, right? And this complex number could be in rectangular form or could be in polar form. So let's say it's in rectangular form, A, B, right? So in this case, z equals a plus jb. This is a rectangular form, right? How do I transform this into polar form? We want to transfer this into polar form. So polar form is as follows, right? In polar form, we represent this number by its magnitude, m, right? And then its angle. The angle between the real axis, positive real axis, and that number, right? So how do I do that? So I want to do, let me write this here actually. So I have a number in rectangular form. I want to transform this to polar form, right? So we said in polar form, the magnitude is just the magnitude of that number. What's the magnitude? We know that the magnitude is a square root of magnitude. This number is just this number times its conjugate square root, right? And we know that is a squared plus b squared square root. That's the magnitude. What about the angle? Oh, but the way we designate the angle in polar form is using this expression, this symbol. This symbol means angle. What's the angle in this case? Well, the angle is theta, but I want to write theta in terms of a and b. Well, clearly tan theta equals b over a, therefore theta equals tan inverse b over a. So the angle is tan inverse, the arctan, the inverse tan of b over a. Okay, so this is the transformation from rectangular to polar representation of a complex number. If you have a complex number in rectangular representation, you can transfer it or transform it to polar representation in this manner. What if I have the opposite? What if I have a number in polar representation already? It's some magnitude and some angle, and I want to transform it back into rectangular form. Right? Again, in this case, again, we can derive this from geometrical considerations. I could take the magnitude and I could project it into the real axis, and then I can take the same magnitude and project it into the imaginary axis. And projection works with sine and cosine, right? If you have, it all comes from trigonometry, right? So if I'm taking this magnitude and I'm projecting it into the real axis, I just take the magnitude times cosine theta, right? If I project this magnitude to the y-axis, I'm just taking the magnitude times sine theta, right? And it all follows from trigonometry, right? So in this case, the real part of the number in the rectangular representation is going to be m cosine theta plus j sine theta. Oh, sorry, it's plus mj. It's plus jm sine theta. Okay, so this is how you do the transformation between the two forms. This is how you transform from rectangular representation to polar, and this is how you transform back from polar to rectangular. Now, having shown you that, I want to now justify my claim that, yeah, although we know how to multiply and add a rectangular representation, multiplication is a bit more hairy than addition. I claim that in polar representation, the opposite happens. Addition becomes harder, but multiplication becomes easier. And I'm going to justify that for you. Okay, so I'm going to assume that I have two numbers in polar representation, right? And I want to figure out how to add them together and then how to multiply them with each other. This is something we have to discuss because we don't know how to do that yet, right? All we know how to do to date is how to add and multiply numbers in rectangular representation. That's it. That's all we know. We know how to transform now the numbers from one representation to the other. We know how to transform from rectangular to polar, but we still don't know how to do addition and multiplication in the polar representation. And the trick that we need to apply to figure that out is to figure out that if I add in the polar representation two numbers, the equivalent number, if I take this equivalent number and then I transfer it back to rectangular, I should get the same number as if I added, I should get the same number that I would get if I added the two rectangular representations. The result of the addition should be the same. If I have two numbers and then I add them and I get a result, I shouldn't get a different result if I do the addition in polar representation. I should always get the same result. So using that fact, I want to move everything back to rectangular because we know how to add and multiply in rectangular representation, right? And that will allow me to derive the formulas for addition and multiplication in polar representation of complex numbers. All right. So I guess let me start with addition. Okay. So to do addition, I need to transform both of those numbers into that rectangular representation, and we already know how to do that. So this is m1 cosine theta 1 plus j m1 sine theta 1, and then the second number comes in, m2 cosine theta 2 plus j m2 sine theta 2. And now I collect the terms. You know, I can do all the I can utilize the distributive property, the commutative property, all of that. I can collect those terms, collect the real parts separately and the imaginary parts separately, and I end up with m1 cosine theta 1 plus m2 cosine theta 2. Notice now, addition is not as straightforward. In rectangular, the rectangular representation, addition was just the addition of the different components. Add the real parts, add the imaginary parts, and then you're done. In the case of polar representation, you don't just add the parts and you're done. You have to do this more complicated thing. You take the magnitude of the first number, multiply it by cosine. You add to it the magnitude of the second number, multiplied by cosine of the angle of the second number. And then the imaginary part is going to be m1 sine theta 1 plus m2 sine theta 2. So addition is the more complicated thing in polar representation. And this is how you add m1 theta 1 plus m2 theta 2 in polar representations, in the polar representation of complex numbers. Okay? Now let's move to multiplication. I'm claiming that multiplication will turn out to be simpler. It will, but you have to know the basic trigonometric identities. Basically, the trigonometric identities that have to do with adding two angles. So if I add and subtract two angles, I can find their cosine or sine. If you know those identities, you know how to multiply two complex numbers. Let me actually, we will utilize those identities to derive the formula for multiplying two complex numbers in polar representation. Let me give you those formulas. So they're very basic formulas in trigonometry. I will not prove them, although it's a very good exercise for you to prove them. Perhaps I'll do that as a homework, right? But they are very basic property. They are very basic properties from trigonometry. So if you remember, so cosine alpha plus beta is going to be cosine alpha cosine beta minus plus. If you have a plus, it will turn into a minus. If you have a minus, it will turn into a plus. Sine alpha sine beta. And then the other identity is sine alpha plus minus beta equals sine alpha cosine beta plus minus, there's no inversion in the sign in this case, cosine alpha sine beta. Yeah. Right? So we should be aware of those identities. And now, being aware of those identities, let's do the multiplication. Let's do m1 theta 1, m2 theta 2. And again, because we don't know how to do this multiplication, yet we know how to do it in rectangular in the rectangular representation, let's switch this to the rectangular representation just to derive the formula. So this is going to be m1 cosine theta 1 plus j m1 sine theta 1. Right, I hope you're seeing where I'm getting here. M2, where I'm going, sorry. M2 cosine theta 2 plus j m2 sine theta 2. Okay, and let's do the multiplication. So take the real component, so this times this, so this is going to be m1 m2 cosine theta 1 cosine theta 2, and then take this term with this term, so j times j is going to be minus 1, and then m1 m2 sine theta 1 sine theta 2. Okay, and then let me take the imaginary part. Imaginary part will come from this term multiplied by this term. So this is going to be m1 m2 cosine theta 1. Is that right? No, that's wrong. Sorry. The imaginary part is going to be from this part times this part. So it's going to be m1 m2 cosine theta 1 sine theta 2, right? Plus the other imaginary component is going to come from this part times this part. It's going to be m1 m2 sine theta 1 cosine theta 2. And you instantly see those identities in here, right? I can take m1 m2 out, and then what do I end up with? I end up with cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. What's that? That's cosine theta 1 plus theta 2, right? That's what this expression is that remains. It's just cosine theta 1 plus theta 2, right? And then plus the imaginary component. I see here I have sine theta 1 cosine theta 1 plus cosine theta 1 sine theta 2. Sorry, sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. That's equivalent to this expression here, which is clearly sine theta 1 plus theta 2. So this is m1 m2 sine theta 1 plus theta 2. So in the rectangular representation, the product is going to be m1 m2 times cosine theta 1 plus theta 2 plus j sine theta 1 plus theta 2. This is in rectangular representation. In polar representation, if I transfer this to polar, this is equal to m1 m2. And what is this? This is the representation of some complex number that has an angle of theta 1 plus theta 2, right? And remember, if we have a complex number with a magnitude and an angle in rectangular representation, it's going to be that magnitude times cosine plus j sine, right? So this is a number with a magnitude m1, m2, and then an angle of theta 1 plus theta 2. So in this sense, we say that multiplication, this is m1 theta 1, is simpler in the polar representation, because all we need to do to multiply is multiply the magnitudes and add the angles. All right, that's it. And we derived this just using the basic trigonometric identities. Okay, so let me summarize. So we have the rectangular representation, we have the polar representation, A plus JB, right? And then M theta. I can transform from the rectangular to the polar by this transformation, right? And then the angle is tan inverse B over A. And the angle could be in radians, could be in degrees, right? It doesn't matter much, but typically in electrical engineering in that form we use degrees. It's just a matter of convention. I would accept both, it's fine, but you have to tell me the units of the angle. If you're using radians, you have to tell me that you're using radians. Right? And then transforming back from polar to rectangular is as follows. It's M cosine theta plus J M sine theta. So that's the transformation. And then the basic operations in both representations are as follows. So in the rectangular representation, addition is as follows. A plus JB plus C plus JD. Simple, is just adding of the terms. A plus C plus J, B plus D. And then multiplication is a little bit more hairy. So it's A plus JB times C plus JD is going to be equal to, take the real parts, going to be AC minus BD plus J BC plus AD. Okay, a bit more terms to calculate. Now in polar representation, we found out that addition is a bit more complicated. So if I have M1 theta 1 plus M2 theta 2, we did this up here. Let me see, what did we find out? Oh, I did not write it as yeah, I found I kept the result in rectangular representation. I did not move it back to polar representation, and I didn't because it's gonna look ugly. Right? It's gonna, like, I have to find the equivalent magnitude, so I have to take this. Actually, it's let me take this expression. Right? So we found out that addition. We said addition is going to be hairier in the polar representation. So we found that the addition is going to let me copy this thing. Draw. I think I can lasso stuff here, and then I can take this. Copy. Right? Say I got this result, but I want to express it in terms of in terms of the polar representation. How would I do that? Let me move this. Okay, so I want to express this in terms of the, I have to remove the lasso. Go back to pen, okay? Right, so I want to, the result of addition, I want to transfer it back into polar representation. Right, so let me keep this in mind. How would I do that? Well, I have to do this, right? I have to, things will get a bit more complex because now I have to take this and square it. I have to take M1 cosine theta 1 plus M2 cosine theta 2 squared, right? Plus M1 sine theta 1 plus m2 sine theta 2 squared, square root. Notice how ugly it is. You do not want to do addition in the polar representation. You want to do multiplication, but you don't want to do addition in the polar representation, right? And then I have to put in the angle. The angle is going to be, let me tag the angle here. So the angle is going to be here. The angle, again, is going to be ugly. It's going to be tan inverse b over a. B in this case is m1 sine theta 1 plus m2 sine theta 2 over m1 cosine theta 1 plus m2 cosine theta 2. It's incredibly complicated, and that's why you do not want to do addition in polar representation. You want to do addition in rectangular representation. So if you're adding two numbers in the polar representation, you just move them to the rectangular representation and do the addition. Right? If you decide you want to later transfer back, you can transfer back. But this is the general formula for adding two numbers in the polar representation. Multiplication is simply, if I have m1 theta 1 times, I like the thickness of this pen better now. I think something changed in the pen when I did the lasso thing. Okay, so this is just m1, m2, theta 1 plus theta 2. Simple. Okay, it will be an interesting exercise to see if we can simplify this expression further. Perhaps we can, I'm not sure, but it will be an interesting exercise to do. All right, but yeah, so typically what you find out when you're solving problems is sometimes you're solving problems in polar representation, and then you're adding two polar representation numbers is a pain. So what you do is you move back to rectangular, and then you add them there. Sometimes you're multiplying a lot of complex numbers, and multiplying complex numbers in the rectangular representation is a pain. So what you do is you transform them to the polar representation, and then multiplying them there. This is a very complex. There is a very common technique that people utilize when they're manipulating complex numbers on pen and paper. Okay, so yeah, the final representation we need to discuss after discussing those two major representations is what's called the exponential representation. It's a representation that utilizes the exponential function, and it turns out to be pretty similar. It turns out to be actually identical to the polar representation. I'll show you why in short order. Okay. It all hinges on a famous formula from mathematics discovered by Euler. You must have heard of it. You probably heard of it. It's called the Euler formula. So it goes like this. You take this exponential function. Exponential function, we know how to deal with it on the real line, right? So we know how to express the exponential function for any input x where x is real, right? And you studied it, you know how to differentiate it, integrate it, and all of that, and you know how to plot it with respect to x. So this is ex. It looks something like this, right? But it turns out the exponential itself could be extended, like many other functions, by the way. It could be extended to beyond the real line. So it could be extended to the whole complex plane. So many functions that we are familiar with from elementary calculus that we defined and derive and work with on the real line, this is the real line, there is a way to extend those functions to the whole complex plane, to the whole plane, right? And when you extend the exponential function to the whole complex plane, you get the generalized exponential function that works on the whole complex plane. It reduces to the so you get, instead of ex, you get e of z, where z is in complex plane, right? So it gives you the same e of x when you are limiting yourself to the real axis of the complex plane. It gives you the exact same exponential function, but then it gives you extra values when you evaluate it at every complex number. In particular, if you evaluated on the imaginary axis, meaning if you evaluate it at complex numbers that are ix, so you're evaluating it at the imaginary axis, this axis here, this is the imaginary axis, you get this famous Euler's formula. So it has this form. It says cosine x. Oh, I diverted back to I. So I have to remember we're in engineering, so we have to use j, right? So e to the power jx is cosine x times j sine x, right? This is an interesting result, and it's a correct result. I'm gonna, I think next lecture I'm gonna give you some justification for this. It's a correct expression that was, discovered by Euler who lived in the 1700s, right? So it's a pretty well-known, well-established result, and it is interesting in the sense that it ties in the exponential function with the cosine and the sine. And one interesting result that you get from this is that if you put x to be pi over 2, right, if you say ei, and instead of x you put pi over 2, what's cosine pi over 2? Cosine pi over 2 is actually put x pi, okay? So what's cosine pi? Cosine pi is minus 1. What's cosine pi? What's sine pi? Sine pi is 0, so this is plus j 0. So we end up with this interesting equation, e to the power I pi plus 1 equals 0. This is a very famous expression in mathematics. It's even designated as one of the most beautiful equations in mathematics. I mean, it's on the surface of it, it looks very intriguing because it's connecting e with I and with pi and with 1 to give me 0, right? 0 and 1 are the first two numbers, and then pi has a very important role in Euclidean geometry. And then I, of course, is the complex constant, complex number, and then e is a number, the base of the natural exponential. Okay, it's the base of the natural logarithm, right? E is a number that's about 2.7 something, I forget. Okay, right. So let's assume that this expression is correct. I'm going to give you the justification for its correctness in the next lecture. But let's start from the point of view that this expression is correct. We know it's correct, right? Someone told us that it's correct. Then it gives us a very curious alternate representation of complex numbers, right? Because remember we said we had the polar representation. I can express the complex number as magnitude and as an angle from the geometrical interpretation of the complex plane. And then I said I can transform this back and forth from this representation back to the rectangular representation by this transformation. So it's just m cosine theta plus j m sine theta. If I take the m out, I end up with cosine theta plus j sine theta. This expression here is exactly this expression here, right? And we know from the Euler formula that this should equal e to the jx. In this case, this should equal m e to the j theta. right? So this is the third representation of complex numbers, which is called the exponential representation. And it's pretty identical to the polar representation. You just have exponential to the power j theta instead of just this symbol, you know. And another thing that's intriguing about it is that it gives you the direct formulas for multiplying complex numbers, you know, or adding complex numbers directly just from the properties of the exponential, right? You know, the basic property of the exponential is that if you have EA times B, sorry, EA plus B, you should get EA times EB. This is a basic defining property of the exponential, right? Of any exponential function, right? So any exponential function, even if it wasn't base E, if it was, let's say, 10 to the power A plus B, that equals 10 to the power A times 10 to the power B, right? Using just this property, we can add complex numbers, sorry, we can multiply complex numbers in exponential form. So, and we get the same thing. Let's say I have two complex numbers, m1, ej theta 1, this is in polar form. Sorry, this is an exponential form, and then I have m2 ej theta 2, and I then multiply them together. I get m1 and m2, and then ej theta 1, ej theta 2. Going back to the exponential property, this property, I can write this as m1, m2, ej theta 1 plus theta 2. This is the same result that we got from the polar representation and the trigonometry, all the complicated trigonometry. We discovered that ultimately things simplify to adding the angles and multiplying the magnitudes. We got the same result much more simply by using the exponential property, the basic exponential property, right? So there is a basic deep connection between exponentials, cosines, and cosine and sines that manifests here, right? We get this. It would have been troublesome if we went to the exponential representation using Euler's formula, and then we got a contradictory result. We discovered that we don't add the angles. We have to do something else other than adding the angles. But turns out we don't get a contradictory result. It's all the same. Whether we express complex numbers in exponential form or express complex numbers in polar form, they are like they are identical forms, really. The exponential form is preferable because it's more mathematical and it's easier to manipulate. Like I said, you can apply easily the properties of the exponential, the basic property of the exponential that I'm outlining here. So you can apply it easily to do your manipulation, right? And then if you want to take a complex number in exponential form and you want to convert it to rectangular form, it's easy to remember Euler's formula. It's easy to remember that ej theta is just cosine theta plus j sine theta. So you just have to remember one formula, which is Euler's formula. Okay, this all, of course, hinges on Euler's formula being true. I prefer not to take it on a matter of faith, although many people do that. So it is possible to have some sort of justification for it, even a proof. So I'm going to sketch the outline of a justification and a proof for it for you next lecture. Right? But I mean, that's it. I mean, we've covered all three basic representations of complex numbers. We have the rectangular representation, then we have the polar, then we have the exponential. Right? I prefer to use mostly when I do my own calculations, I prefer to mostly use exponential or rectangular. Polar does exist, and it's used a lot in electrical engineering, right? But it's not, it depends on the subfield of electrical engineering. Like if you were studying DSP or communications, comms, you would see more rectangular and exponential representations of complex numbers. If you're studying something like power transmission and distribution, you would see more of the polar representation. So it depends on the subfield of electrical engineering that you're studying. For example, in studying transmission lines and power systems, you would see polar a lot. If you're studying DSP, you would see exponential representation a lot. So it doesn't matter. You should just be aware that polar and exponential is identical. You can express complex number as either m ej theta or m theta. It's the same thing, right? One big difference, though, you have to be aware of is that when you express it in this form, theta here is always in radians. Has to be always in radians for Euler's formula to be true. If you express it in this form, theta is mostly in degrees. That's what you would see in textbooks or literature that represent complex numbers in this form. You would see theta written in degrees instead of radians. Okay, that's the only thing you have to be aware of. All right, so I think we're pretty much done with the introduction to complex numbers. I think next time what we will do is, like I said, I'll give you the justification for Euler's formula, and then we're gonna do some examples and move on. All right, thank you guys.